Hey, welcome back. We're going to go into 12.5 now, arc length and curvature. We've seen arc length before, and so hopefully this won't be too mind-blowing. Let's introduce it. Okay, so section 1, arc length, and we're worried about arc length of space curves and plane curves. Recall your work from Calc 2. We initially introduced the arc length formula as the integral from something like a to the b of the square root of 1 plus the derivative squared dx. And then we were able to convert that using our definition for derivatives with respect to some parameter t. So we had parametric equations, and then we were able to define the derivative and then do a substitution into this formula, and we ended up with the formula integral a to the b of the square root of the components derivatives squared. And that turned out to be kind of the same spiel. Do sort of some substitutions and a bit of arithmetic, and you end up with this formula. Okay. This is basically the same formula that you'll use now if you're in Calc 3, because you're given some sort of space curve, and the components are basically just the components of the parametric equation, right? So let's say I have a space curve. Now let's just keep it plane curve. X of t, comma y of t. So to get the arc length, S, it's the same formula. Okay? S equals the integral from a to the b of the square root of x prime of t squared plus y prime of t squared. The kind of cool thing now is that we can rewrite this formula, noting that the integrand here is basically just the magnitude of the position vector, right? So I can rewrite that as the magnitude of the derivative of the position vector dt. And from this, we're going to be able to get some nice relationships throughout the rest of the book. So anyways, Theorem 12.6, they give you the same formula, but for a space curve. So then it's just an extension. You add one more component in there and take its square, and then you get this nice formula here on the right. Let's take a look at finding arc length given this thing. So example 1, we have r of t is t, comma 4/3 t to the 3/2, comma 1/2 t squared. Example 1, we want to go from 0 to 2. Okay, they give you a picture of it. Let's not look at the picture. I don't want to see the answer. Right? So anyways, to pull this off, we need the derivative of this thing. So we have 1, then 4/3 t to the 3/2 minus 1 is 3/2 minus 2/2, which is 1/2, and then of course we brought down a 3/2 for the power rule. I almost accidentally integrated there. Here, bring down the 2, and then you have t to the 2 minus 1, which is just 1. So we have 1, comma, these guys cancel, so it's another 2t to the 1/2, comma t. Okay. So for our arc length, I'm just going to do s. That's my cursive s, in case you've never seen one. The integral from 0 to 2 of the square root of those components all squared. So 1 plus 4t, right? Squaring that second component, 4t plus t squared dt. And then I got to integrate that thing. Let's make sure everything was done correctly in the first place. Here's minus 1. Yeah. Down. Yeah. Okay. Everything looks hunky-dory. As far as integrating that thing, I honestly have no clue. So I must have done something wrong, right? So we can't integrate it. It's probably because there's something wrong with it. Yeah, they use integration tables. Yeah, okay, well, from Formula 26, apparently. Oh, jeez, I accidentally hit a little button there, sorry. So let's hit the Formula 26 to get this. I'm going to have to complete the square on top of it. It's P. It's one of these characters here. Yeah, there it is. Okay, so let me complete the square. Sorry, I didn't envision. I don't think none of the homeworks are like this. Okay, they're not gonna. Okay, so I have to complete the square. I got t squared plus 4t plus 4 all over 2 squared, which is 4. Immediately subtract 4 plus 1 dt. So I have the square root of t plus 2 squared minus 3 dt. And then we're using this formula 26. So in my case, u is t plus 2. And then my a value is square root of 3. So this should equal 1/2 times t plus 2 times the square root of t squared plus, this whole thing, which would just be t squared plus 4t plus 1. Then it's plus or minus, right? So it's minus in our case, just going backwards, I can get there. Then minus a squared, so minus 3 ln, absolute value. 3 ln, absolute value of u. Now my cat's getting in on the action. You must be able to tell I'm stressed. I'm going to give you more stress. It's 2 plus again the square root of t squared plus 4t plus 1. And then we have to evaluate this thing. Surreal. Okay, I take their word for it. It's it is what they say it is. They've distributed the 1/2 in their answer. And evaluate it from 0 to 2. And apparently you get 4.816 of that. Okay, great. So there's that. Let's look at example 2, see what's going on there. Find the arc length of a helix. Okay, so I don't know how far. Find the length of one turn of the helix. Okay, so I think one turn means we're going to have to go full circle. So from 0 to 2 pi. Take a wild guess. That's what they want. R prime then. Negative b sine t, comma b cosine t, comma square root 1 minus b squared. And then I go to my integral, so my arc length from 0 to 2 pi is the square root of b squared sine squared t plus b squared cosine squared t plus 1 minus b squared dt, which will equal the integral of the square root of b squared times sine squared plus cosine squared t plus 1 minus b squared dt. Sine squared plus cosine squared, that's just equal to 1. It's one of our Pythagorean identities. So you get b squared plus 1 minus b squared dt, which is just the integral of the square root of 1, which is just 1 dt, which is equal to t from 0 to 2 pi, so it's equal to 2 pi. Okay. Okay, great. So pretty simple. The next part is this stuff about arc length. You could basically use a dummy variable and produce a function in terms of t that tells you the arc length if you're so inclined. The advantage of the arc length parameter, you're going to see it lessens computations when you're doing things like finding curvature, which we're going to be doing in a couple seconds. It also makes some of these integrals easier if your formula is in terms of arc length. The inside of the integrand is just going to be 1. So the magnitude of the derivative of the position function with regards to arc length will always be 1. So you see that right here on the right. Okay. And then if you integrate, it's basically you just end up with the length of the interval. Okay, so first we want to produce this formula S of t, and there's a nice little exercise in the homework that kind of walks us through it. Is there an alternate form of this? No, so we just have to go, this is 5. Let's go ahead and make this the video quiz while we're at it. Let me write this down. I'll be this video quiz set number 3. We'll basically have 5 questions in it, and 12-1, 12-2, 12-3, 12-4, 12-5. Okay, so this question is number 5 in WebAssign. I'm just putting it in my notes so I know when you send it to me. Okay, so video quiz, video quiz, video quiz. Okay, so the function given r of t is 2 cosine t, comma 2 sine t. Somebody in my office hours. No. 2 sine t, t. And what do we want to do? Write the length of the arc S on the helix as a function of t by evaluating the integral below. Okay, so one thing we need to do is so we're looking for this function S of t, and to find it, we're going to integrate from 0 to t, and we're going to put a dummy variable like u. Okay, the book uses u, so du. So I'm going to need the derivative. R prime of t is equal to negative 2 sine t, 2 cosine t, and then 1. So plugging the squares of those into the square root here, I have 4 sine squared, and I'm going to use my dummy variable u, and then plus 4 cosine squared u plus 1. Okay. And then use your Pythagorean identity to simplify that a bit. So you can factor out the 4, and you just get sine squared u plus cosine squared u plus 1 du. And then sine squared plus cosine squared is just 1. So you just have 4 plus 1 in there, which is 5. Right? So you get square root of 5 du. Integrate that with respect to u, square root of 5 u, evaluate from 0 to t. That will give you square root of 5t. So what you end up with is a formula for arc length in terms of t. So S of t in particular equals square root 5t. That thing, the square root 5t, we can then plot back into the original function and have an R of S formula. Okay. So in part B, that's what they want you to find. They want you to solve for t. I've kind of done that. I'm going to solve for t. So t must be S of t all over root 5. And then I'm going to take this thing and dump it back into R of t. Okay. So that will give me R of S. So this was part A here. Okay. And now I got part B. And reminding me of a, okay, sorry, sort of multitasking. Right, so where were we? Part B, yeah, rewrite the R of t function with this new parameter s. So R of s will equal 2 cosine of s over root 5. So you're just replacing t in this formula up here. R of t is 2 cosine t, so instead of 2 cosine t, you have 2 cosine of s over root 5, then you'll have 2 sine of s over root 5, and then t is just s over root 5. And that would be your R of s. Find the coordinates on the point on find the coordinates of the point on the helix for the following arc lengths. So part C, s equals root 5, and then s equals 4. Well, this is just plugging stuff into my R of s formula. So R of root 5 is going to be 2 cosine of 1, whatever that is, use your calculator, 2 sine of 1, and then I think it's just 1, right? I lost, I can't see what my thing says anymore. Yeah, root 5 over root 5 is 1. Plug in 4, s of 4 is going to be 2 cosine of 4 over root 5, need a calculator for that. 2 sine of 4 over root 5, need a calculator. And then just 4 over root 5. Okay, so one of the magical things about this new formula, this R of s thing, is that the magnitude of the derivative is always equal to 1. Okay, so part D, they want you to show that the magnitude of the derivative of s, show that it's equal to 1, right? Okay, so let's figure that out. So the magnitude, first we need the derivative, right? So r prime of s, that's going to be negative 2 sine of s over root 5 times 1 over root 5 from the chain rule. So I get negative 2 over root 5 sine of s over root 5. The next guy, similarly, 2 over root 5 cosine of s over root 5. And then the last component would just be 1 over root 5. Okay. Then I'm going to square all those and get the magnitude of the thing. And of s is going to be square root of, the first guy squared would be 4 over 5 sine squared of s over root 5, plus the next guy is 4 over 5 cosine squared of s over root 5. And the last guy is just 1 over 5. Again, you could factor out and take advantage of Pythagorean identities, noting sine squared plus cosine squared is just equal to 1. Plus 1 over 5. So you'd end up with the square root of 4/5 plus 1/5, which is equal to the square root of 5/5. 5/5, of course, is 1, and the square root of 1 is just 1. Okay, okay, so believe it or not, that is a good thing, because if in certain cases it will help you with computations. So if you remember how nasty finding the unit normal vector was, this thing, believe it or not, in certain circumstances can help you reduce the number of steps that you have to end up having to take. Okay, so anyways, once you do that, if you are looking for arc length, then if you have it in terms, so also if you're given the formula in terms of s, finding the length of the arc is real easy, because the integrand will just be 1, and the length of the arc will just be the length of the interval that you're integrating over. Okay. So anyways, yeah, there's that. Okay, so arc length. Curvature is the next issue on the chopping block. So curvature is kind of the rate of change of the unit tangent vector So 2 curvature K is the magnitude of the rate of change of the unit tangent vector with respect to arc length. We could rewrite that as just T prime of S if you have it in terms of the arc length parameter. If not, you may have a lot of work to do in finding basically the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the position vector, and they get worse and worse. There's more and more of these formulas. I'll just leave it to the book at this point. So there's some of them, so cross products involved. You can also have them in terms of functions. Okay. These are the equations that I'm giving you on the formula sheet for the next test. Let's see if I can find where they are. It's basically the formulas I'll give you are these. You need the tangential component formulas. I'll give you those. The components of acceleration. I mean, those. The a sub t and the a sub n. Those I'll give you those, and then I'll give you all the formulas for curvature. Okay. All right. So let me go back to where I was. So again, it's the rate of change of this unit tangent vector is the way you can kind of think of it. So when you go really close to a corner, you could see the unit tangent vector is changing more rapidly in its direction than it would be out here where the line is going straighter. See how the unit tangent vectors are pretty much the same as you go further down. But on the corners, that unit tangent vector is changing rapidly. And that would have high, so the curvature would be high on the corner, but then it would slow down as we get in a straightaway. Okay? And that's basically what you're talking about in a nutshell. So anyways, let's look at one. Here we're finding the curvature of a circle, basically just showing that the curvature is this constant 1 over the radius. So example 4, curvature of a circle. I guess we can make a vector valued function to represent a circle with radius 1. We don't have to do that. We could just put an R here. Hate to use R because we already have an R, but an R sine of theta. So, if you put that back into rectangular coordinates, that would be a circle with radius R, right? Because x would equal R cosine theta. So x over R would equal cosine theta. Y would equal R sine theta. So y over R would equal sine theta. And then from the Pythagorean identities, cosine squared plus sine squared, theta equals 1. And then substituting in, we get x squared over r squared plus y squared over r squared equals 1, multiplied through by r squared, and you get a circle with radius r, okay, centered at the origin. We want to find the curvature of this thing, and we have a boatload of formulas we can use to pull this off. I don't think I'm going to you could get the, sure, let's get the thing in terms of S. Okay, so remember, we could figure out S of t by kind of just integrating from 0 to t. I'm going to need to take the derivative of this to pull this off. R prime of t is going to be negative r sine theta comma r cosine theta. So this will be the square root of r squared sine squared theta plus r squared cosine squared theta. I guess d theta, we don't really need a different variable. This material here would just end up being r squared, right? Because you can factor out the r squared, you get sine squared plus cosine squared, that's 1, and then you take the square root of r squared and you just get r d theta. And then integrate that with respect to theta, you get r theta, evaluate from 0 to t, that will just be rt. So you can always rewrite this formula, s of t equals rt. Well, it's not much of a difference, is it? It's t you could replace with then s over r, right? So I can go back to my original vector value function and have r of s now. So that'll be r cosine of used to be t, now it's s over r, comma r sine of s over r. And then to get the curvature, I need basically the unit tangent vector. And so to get t of s, that's just going to be the derivative of r of s divided by the magnitude of the derivative of r of s. But the magnitude of the derivative of r of s is just equal to 1. Okay, so t of s is just going to be r prime of s, right? So t of s will just be negative r sine s over r times 1 over r, so it'd just be a negative sine of s over r, and then r cosine s over r times 1 over r, which would just be cosine of s over r. Okay. I actually need the derivative of this thing then with respect to s, right? That's the curvature formula you see on the right. So one formula for curvature, it's just the magnitude of the derivative of the unit tangent vector with the arc length parameter s. Okay, so t prime of s then is going to be negative 1 all over r cosine of s over r, comma, negative 1 over r sine of s over r. Okay. So really there's somebody at my door. Okay, so anyways, then I need the magnitude of this guy, and that will be the curvature. So the magnitude of t prime of s is going to be the square root of 1 all over r squared cosine squared of s over r plus 1 all over r squared sine squared of s over r. Then you can factor out the 1 over r squared. And again, take advantage of the Pythagorean identities. So you have cosine squared s over r plus sine squared of s over r. This junk will be 1, so you just end up with the square root of 1 over r squared, which of course is just 1 over r. So that being the curvature of a circle. Okay. Right. Oh, they did the same thing I did. Okay, that's awesome. All right. We're talking about the curvature of a straight line of 0. That's great. We have some other formulas for curvature given in Theorem 12.8. So usually I don't do this process where I solve out for s and rewrite the original vector value function in terms of s. I generally don't do that, to be honest. And actually I see a mistake. This should be r of theta, right? It's in terms of theta. But anyways, there's that. They give you some more formulas for curvature. Let's look in the exercises and kind of see what we're up against there. And they also are able to put one application here. They're able to rewrite the acceleration in terms of unit tangent vector, the principal unit normal vector, and curvature. So you can rewrite it that way. Let's see. Okay, so here's the formula page. Like I said, I have on Blackboard, I put out the formulas that I'm going to allow you to use on the second test. So you go to, your home page, wherever that is. I guess I already got it open. Go to your home page. go to the blackboard and go to courses and go to Calc 3 and course content. And then for test 2, I'll allow you to use these formulas. So you either can print this out or make a copy by hand and for the test. So you see there's a ton of curvature formulas that you're dealing with. So it becomes like a pick your poison type problem. Which formula do I pick so I can sleep at night, you know, so I have enough time to go to sleep. It's like that. And okay. Anyways, let's look at some of the homework problems and kind of just. Okay, so a lot of them, you see the answer is 0. That's just because these are straight lines, and the curvature of a line is 0, so it works out that way. Let's look at number 9. Find the curvature of K for the given parameter. So R of T is T, 1/9 T cubed, and we're looking for T equals 2. Okay, so let's go over to my formulae. The second set of formulas here, you see they're given if your curve is given by a function, like y equals f of x or a parametric curve. The 3 on the bottom are the ones we're going to be using. So I hate getting the principal unit normal vector, so I'm going to kind of almost cross out that third formula and never use that. But the second formula is fair game. Okay, let's get R prime and then do the cross product with R double prime. See how that works for us. Okay, so R prime is 1, 3/9 T squared, so that would be 1/3 T squared. R double prime is then going to be 0, 2/3 T. And you can do a cross product. Is it really even necessary to go that far? Can we just let's not do the cross product. Let's get the T prime of T going, right? So T of T is just R prime of T over the magnitude of R prime of T. Okay, we have the R prime of T there. I need the magnitude of R prime of T. So R prime of T's magnitude is the square root of 1 plus 1/9 T to the 4th. You can kind of rewrite that and simplify it. So that would be 9 plus T to the 4th all over 9. And then that would be square root of 9 plus T to the 4th over 3. And then we're multiplying the reciprocal of this times this thing, and that will give us the unit tangent vector there. So we end up with 3 all over the square root of 9 plus T to the 4th. Oh, this doesn't look like it's going to be a lot of fun. T squared all over the square root of 9 plus T to the 4th. All right, then I need to get its derivative, and I'm already regretting it. Oh man, whatever, brute force it. T prime, so the first guy is going to be -3 times 1/2 times 9 plus T to the 4th to the -1/2 minus 1 is -3/2, and then the chain rule, so I got 4T cubed, comma, see I just chose the wrong formula. This is what happens. I'm getting punished for it. The other guy, low D high, so 9 plus T to the 4th to the 1/2 times 2T minus high D low. T squared times 1/2 times 9 plus T to the 4th to the -1/2 times T 4T cubed all over the low squared, 9 plus T to the 4th. Let's clean that up. first guy then. 2 goes in the 4 2 times, so negative 6t cubed all over 9 plus t to the 4th to the 3/2, comma, I'm going to multiply top and bottom of this guy by 9 plus t to the 4th to the 1/2. So in the top, that will be 9 plus t to the 4th times 2t minus the 9 plus t to the 4th will go away, and you have 1/2 and the 4 is 2, so minus 2t to the 5th all over 9 plus t to the 4th to the 3/2. That will be negative 6t cubed all over 9 plus t to the 4th to the 3/2, comma, and then this will be 18t, and then you got 2t to the 5th minus 2t to the 5th, those will go away, t to the 4th to the 3/2, and then the formula says I got to put it over r prime of t, the magnitude of r prime of t. So I kind of already figured that out. That was this thing, 3 all over square root 9 plus t to the 4th. When I take its reciprocal. So I need the magnitude of that thing. See, man, this is just a freaking nightmare. So I'm not done yet. I need the magnitude of the derivative of this thing. So let's see what happens. So this guy is 36t to the 6 plus 18 squared, whatever the heck that is. 18 squared is 324 apparently, plus 324 t squared all over this 9 plus t to the 4th to the 3rd power. You could probably factor 324. So what is 18 squared? There's 9. Is there enough in there? 4 divided by 36. Yeah, there is. So this will be 6 times the square root of, and you can factor out a t squared as well, so that would just give you a t. Then this will be t to the 4th plus 9, which will nicely 9 plus t to the 4th cubed, should be 6t all over 9 plus t to the 4th, believe it or not. And then the magnitude of the other thing was 3, the reciprocal of it was 3 over square root of 9 plus t to the 4th, because what we're looking for is the magnitude of t prime of t all over the magnitude of r prime of t. And this thing here is the reciprocal of the magnitude of r prime of t. So for our curvature then, it's 3 all over the square root of 9 plus t to the 4th times 6t all over 9 plus t to the 4th, which will equal 18t all over 9 plus t to the 4th to the 3/2. My gosh. I wanted to figure out the curvature at 2. I complained a lot. I am sorry. I just wasn't expecting it to be like this. 9 plus 4, 8, 16 to the 3/2. That'll be 36 all over 25 to the 3/2 is 125. And it's going to be wrong, right? That's my reward here. 36 over 125. 0.288. Huh. Can't believe that's right. Yeah, I would advise not doing it using at least that problem. The cross product was probably a lot easier. I didn't want to do the cross product because my brain freaked out that there wasn't 3 components, but you just make 0 the 3rd component and you can take the cross product. Sorry. All right. So anyways, what else? Yeah, sure. Let's look at some of these ones where they give you a function, and then you got to figure it out. So number 13. I have maybe one of these other ones would be better. Sure, number 16, let's try that guy. Or I don't really care which one we try. 16. Okay. So this time they give you y equals 2 minus x to the fourth. They want you to find all points on the graph of the function such that the curvature is 0. So basically you need to build a curvature function in terms of x, and then you could go from there. So the formula is going to be this guy, double prime all over 1 plus y prime, and then square this, and then all that to the 3 halves, okay? So you need y prime, that's negative 4x cubed, and then you need y double prime, which is negative 12x squared. That's an absolute value. That's no longer talking about magnitude. We're back in our friendly world of regular math. So y double prime, absolute value of is 12x squared, all over 1 plus y prime squared. That's going to be 16x to the 6 to the 3 halves. They want to know where the curvature is, the points where the curvature is 0. You just set this thing equal to 0. So you got 12x squared all over 1 plus 16x to the 6 to the 3 halves equals 0. That denominator isn't going to affect your answer, so you just multiply both sides by it, and you get 12x squared is 0. So it seems the only solution is x equals 0. So the point on the graph where the curvature is 0 is going to be at 0, comma, and you plug 0 into here, and it gives you the y component, right? So y equals 2. So we can find it, 0, 2. We got some applications in there. Let's try number 15. Consider the following. So y equals ln x. Find the curve on the point. Find the point on the curve where the curvature is maximum. So this is going back to Calc 1, where you're taking derivatives of a function, find the critical points, etc., etc. First, we need to get the curvature function. So again, I'm going to need y prime, which is 1 over x, or if you'd rather, x to the negative 1. Then I need y double prime, which is negative 2x now to the negative 2. And so my curvature formula, the absolute value of y double prime is 2 over x squared, and then all over 1 plus y prime squared, which will be 1 all over x squared to the, what is it, 3 halves. Okay. So rewriting this a little bit, it would be 2 all over x squared times, and we could probably rewrite this a little, x squared plus finding a common denominator 1 all over x squared to the 3 halves. And then rewrite that, so 2 all over x squared times x squared plus 1 to the 3 halves, and then x squared to the 3 halves, and the denominator of the denominator is going to be x cubed. So you have it all over x cubed. So you know, this will divide in this, leaving you with just an x, and then if you do a reciprocal, you get 2x all over x squared plus 1 to the 3 halves. Okay. Okay, so to find the maximum of that thing, you need to take its derivative. So k prime is going to be low d high, so quotient rule. That's what I mean when I go low d high minus high d low. So low is x squared plus 1 to the 3 halves. D high is 2 minus high times the derivative of the low, so that's 3 halves times x squared plus 1 to the 3 halves minus 2 halves is 1 half, and then the power rule 2x all over the low squared, so x squared plus 1 now cubed. We can factor out x squared plus 1 to the 1 half. So I don't see how much help that's going to do for us. Well, let's try it. So x squared plus 1 to the 3/2 is going to leave us with an x squared plus, or rather to the 1/2 here. You factor that out, you get x squared plus 1 to the 2/2 times 2 minus, these will cancel, so you get just 6x squared, I think. So, right? X squared, and 3 times 2 is 6. Okay, all over x squared plus 1 cubed, and then we want to simplify that stuff. So 2x squared plus 2 minus 6x squared is going to be 2 minus 4x squared all over x squared plus 1 to the 5/2 when I bring down the 1/2. And then you set that equal to 0. The denominator, again, isn't going to really affect things, so you just set the numerator equal to 0 and solve. So you have 4x squared equals 2, so x squared equals 1/2, so x equals plus or minus square root of 1/2, which is 1 all over square root of 2, if you will. You could do a number line type spiel, negative 1 over root 2, positive 1 over root 2. And so for big numbers, negative, it's going to be positive. For 0, now I'm plugging things into this formula. Okay. For 0, it's going to be, it's positive again. Big number negative, oh, that would be negative. And then big number positive would end up being negative. So it's going down, then up, then down. So the maximum is going to be right here at x equals 1 over root 2. So to get your coordinate, you just take 1 over root 2 and plop it into here. So that ordered pair would be 1 over root 2 comma ln of 1 over root 2. And you can see that's what I got as my answer. Then finally, they want to know the limit of the curvature as x goes to infinity. So you take your curvature function right here, and you take the limit as x goes to infinity. So let me borrow that and bring it down to the bottom so we can do this process. Okay, so there's that. I'm going to take the limit as x goes to infinitar. And yeah, so with these limits, when you're doing limits of kind of like quasi-polynomial functions, you can just kind of look at the high degree parts. So in the top, the high degree term is just the 2x. In the bottom, you can kind of just cheat a little and look at this part. So x squared to the 3/2 is x cubed. And then that will be basically the limit of 2 all over x squared. That will be some L over infinity, which will be 0. So the curvature will go to 0 over time. Okay, so let's leave it at that. That's more than enough fun for one day. As usual, thank you for watching. Make sure we got the video quiz. There it is. Okay, we should be good. Okay, see you next time.